this lesson then we're going to be looking at equilibrium. When there's equilibrium in a system of forces, then there are two things. One is the resultant force in any direction is zero. So in any direction, the forces in one direction will be cancelled out by the forces in the opposite direction. And the moment about any point in the system is 0 Newton meters. So that is what we mean when there is equilibrium in a system of forces, and we're going to use both those things in the following examples. So here in example 1 we've got Dastardly and Mutley on a seesaw type situation, and the first thing to do is identify the sources of forces, and we're looking at the forces on the rod. Well, straight away the rod has a weight. We don't actually know, we're not told in the question how heavy the rod is, so we just mark on its weight, W, and that acts in the center of the rod because it's a uniform rod. Now, Dastardly weighs 80 G newtons. Now that force, you can see that 80 G isn't actually Dastardly's weight, it's a normal contact force. Because Dastardly is in contact with the rod exerts a force on Dastardly and he exerts an opposite force, and that opposite force is 80 G. And the reason it's 80 G is because his mass is 80 kilograms. But it isn't a weight force, it's a normal contact force. The weight of Dastardly will only act on Dastardly. And similarly for Mutley, he weighs 20 kilograms, so he will exert a normal contact force on the rod of 20 G newtons. And finally, that rod is resting on the pivot, so there's a normal contact force from the pivot on the rod, R, and that's acting upwards. So we've now identified all the forces on the rod. Equilibrium, as we said earlier, means we can take moments about any point and we get 0 as our resultant moment. Now, because I've got unknown forces W at M, I'm going to take moments about M. And when we take moments about M, any force that acts through the point M has no moment because its distance from that point is 0. Therefore, R will not have a moment about M and W will not have a moment about M. So they disappear. So now if I take clockwise moments, the clockwise moment is exerted by the 20 G times by 2 meters. And Dastardly is exerting an anti-clockwise moment, and that anti-clockwise moment is 80 G times by, and we want the distance from Dastardly to the point of pivot. Well, that whole distance there is 2 meters. This distance is x, which means this actual distance must be 2 minus x. So it's 80 G times 2 minus x. A little bit messy, but that's the expression we get for the anti-clockwise moment. Now, because we're in equilibrium, the anti-clockwise moment must equal the clockwise moment. So 40 G equals 160 G, subtract 80 G times x. We can divide through by G because each of the 3 terms has got a G in it. We can divide through by G and rearrange to give us 80x equals 120. So x equals 1.5 meters. And I recommend then you turn to exercise 4C and have a go at questions 3, 4 and 5. You might want to pause the video because I'm going to press on with the next section. In this next section we've now got 2 supports, and again we have equilibrium. Now, this is taken from example 6 in the book. So we've got the rod 3 meters, we've got the supports A and C set up as shown, and we're trying to find the magnitude of the reaction at each of the supports. So again, sources of forces. Let's put the forces that are acting on the rod. Well, its weight is 20 newtons, and that's acting right in the middle of the rod because it tells us it's a uniform rod. So that will be 1.5 meters from A. We've got a reaction force at A, which I've just called RA, and we've got a reaction force at C, which I've called RC. And those are the three forces acting on the rod. Equilibrium means taking moments about any point gives 0 Newton meters. So I'm going to take moments about point A. If I do, taking moments about point A, the reaction force at A will disappear because the reaction force at A passing through A has no moment. Therefore, the clockwise moment is 20 times 1.5, and that's 30 Newton meters. The anti-clockwise moment is given by the reaction force at C, so that's R at C multiplied by 2 meters. And because it's in equilibrium, those two things are equal, and therefore we can calculate the reaction force at C to be 15 newtons. So we've now marked in the reaction force at C as being 15 newtons. And remember, equilibrium isn't just about moments, it's also about the resultant force in any direction. So if I resolve vertically, all the upward forces should equal all the downward forces. So the reaction force at A plus 15, those are the upward forces, equals the 20 newtons acting downwards, and so the reaction force at A is 5 newtons. Here in example 7, once again, let's put the sources of forces. What are the forces acting on the rod? Well, its mass is 40 kilograms, so the weight of it is 40 G newtons. There's a normal contact force created by the person standing at point E. That person weighs 80 G newtons. There's a reaction force at the support C, which I've called Y, and it tells us that the reaction at D is twice the reaction at C, so I'm going to mark on the reaction force at D as being 2Y. So now I have all my forces acting on the rod. Equilibrium means the resultant force in any direction gives 0, so the upward forces are Y plus 2Y, and the downward forces 120 G, and that means Y equals 40 G newtons. So therefore I put Y and 2Y in on my diagram. And equilibrium means taking moments about any point gives 0 Newton meters, because this is going to help me find the distance from A of the person which we've marked on at E. So if we take moments about C, the 40 G resultant reaction force has no moment about C. So the clockwise moments are given by 40 G times 1.5, and then 80 G times by that distance D, which we don't know. So I'll just write that as 80 GD. The anti-clockwise moment is given by the reaction force at D, and that's 3 meters away from point C, so it's 80 G times 3, and that's 240 G Newton meters. Because we're in equilibrium, the clockwise moments equal the anti-clockwise moments, and therefore 60 G plus 80 GD equals 240 G. We can divide through by G, and therefore from that we will find that D equals 2.25 meters. Now remember, D is a distance from E to the support C, so the distance from A is 3.25 meters. And hopefully you've understood all that, which means you can turn to exercise 4C and have a go at question number 8. In this example where the rod is suspended by wires, although it's different from the previous example with the two supports, once we put the forces on, the force diagram is exactly the same. So what you have to understand is that the wires are in tension, and it tells us that these tensions are going to be equal. Therefore, we have to mark on a tension force at A and a tension force at C. So now our force diagram looks like that. Equilibrium means the resultant force in any direction gives 0. So vertically, we've got 2T upwards and 90 newtons downwards. So T equals 45 newtons. Equilibrium means taking moments about any point gives 0. We're going to take moments about point C. And the clockwise moments, when we take moments about point C, are given to us by the 50 Newton force that will turn the rod in a clockwise direction about point C. But also the tension here at A will want to rotate the rod clockwise about point C. So the 50 newtons and this tension here are working together to produce a clockwise moment. So that's the tension times 2.5, 2 meters plus the 0.5, 2.5, and then 50 times x. That gives us 112.5 plus 50x. And the anti-clockwise moment is given to us by the single force of 40 newtons. So it's 40 times 0.5, and that's 20 Newton meters. Clockwise moment equals the anti-clockwise moment, which gives us 112.5 plus 50x equals 20, and that gives us x equals negative 1.85. Now, x equals negative 1.5 seems unusual that we have a negative distance, and all that means we can interpret that as being 1.85 meters, not to the right of C, as the diagram suggests, but to the left of C. And consequently, our true force diagram actually looks something like that. Now, we couldn't have known that to begin with. We were trying to find the distance of where the 50 Newton force should be placed. It just so happens I speculated it would be to the right of C, but in actual fact it's to the left of C. So I hope you've understood the example of suspended by wires. Have a go now at exercise 4C, questions 6 and 7.